RC cars that you can buy at Christmas time that are 1/20th scale? Can you buy some that are even smaller than that? Yeah, they have these little things with a little glass, not glass, but plexiglass bubble over it, and a little bitty car inside there, and that's probably a 1/50th scale, okay? It's a really small one, but you can put it on the ground and you have this little controller that you can drive it all over the place. So you need to decide, the team needs to decide, if we're starting at this point, how big do we want this thing to grow? How small do we want it to grow? Do we want it to vary infinitely between those limits? Do we want it to vary only in certain sizes? If you say, we're going to vary it only in certain sizes, it's pretty easy. You set up a parameter right at the very beginning that says, if I put a 1 in, that 1 is going to be the original size. If I put a 2 in, it's going to go to a 1/4 scale model. If I put a 3 in, it's going to be an 8th scale model. If I put a 4, 5, whatever number I put in, it's going to go to a fixed size, and all that does is cue up a length to your car, a track width to your car, and an overall height. And off of those 3 little parameters, you can drive virtually everything else. Who gets to decide? We already decided that, okay? Remember, this is your project. It's not Dr. Jensen's project. This is your project. And each, need to decide, how am I going to take what's lectured in class, what's demonstrated in the lab, how am I going to apply that on this project? It's how and how much, and that you get to decide. I think if you read the project report, or the project proposal that we passed out at the beginning, it suggests that for every member of the team, they ought to have at least one part be fully parametric. Okay? Maybe you only have one subsystem that the whole team works on and makes one subsystem really parametric. Okay? But again, it's your call. You need part parametrics, you need assembly parametrics, because those are things that we lecture on and have talked about in class. Okay? We're now talking about topology optimization. How much topology optimization do I put into the project? Well, a minimum would be 1 example per team member. So you'd have 3 examples of topology optimization. Could you have 25? Well, if there's enough time, do that. But then don't tell me, Dr. Jensen, we didn't do this and this and this and this because all we did was topology optimization. You have to kind of blend all of these topics together into your project. You should combine good engineering with the use of these applications that we're kind of talking about. And so you don't just do it and say, I'm going to throw in these kind of loads and these kind of constraints, and they're just not even realistic loads and constraints. Because at the end of the optimization, what are you going to have? It's going to be a useless part. It'll either have no mass because the loads were so light that it could eat everything away without, needing anything there, or the loads were so large it can't remove anything because of the stress levels. Okay? And this is what I want you to keep foremost in your mind. It's not my portfolio piece. It's your portfolio piece. At the end of this class, you will have something that very few students going through a university doing mechanical engineering will be able to walk away with. Okay? You will have a CD or a DVD that has lots of examples of doing engineering using modern tools. Okay? So that's the goal. The goal is to give you something that you can walk away with and show off to potential employers. So where do I begin? Well, I just grabbed this out of one book. I'm not sure which one it was, but I grabbed it out of one.
The 69 Camaro.
Okay, it's the Camaro. So I grabbed this. This is the sheet that kind of shows the basic layout of everything. What is this thing right here? That's the bill of materials or parts list. Okay, so the first thing that I did is I kind of counted up these things, and as I counted them up, I found that there was approximately 90. I think it's 87, if I remember the right number right. 90 parts, assuming that I have a normal team of 6 individuals. I divide that up and I say each person has at most kind of 15 parts just from doing this kind of cursory thing. The next thing I did is I said, how long is it going to take me to measure some of these parts and to sketch it so that I can have the measurements on it? Well, I'm assuming it's going to take about 15 minutes to do a freehand sketch and to pull off measurements. Do I have to try and measure every little chamfer, every little fillet, every little round, every little groove and slot? Do I have to try and measure that kind of detail? No. Okay. If it's buried under the hood, you can use some latitude. You're the engineer. You can use some latitude to change these things. You're not trying to make it a perfect Xerox of this vehicle. So based on that, maybe there's 4 hours of me measuring parts, sketching them, trying to figure them out. Okay? Assume an average of 1 hour per model. Now you'll see in a second that if it takes you 1 hour to do the motor, or 1 hour to do the controller, not the big controller, but the solenoid box. If it takes you 1 hour to do that, you've long since forgotten your CAD or something, because those things ought to be 5-minute, 10-minute models, okay, to build. So maybe there's 15 hours total in the modeling. Well, the remaining time in this semester should be done focusing on what? It's all of the engineering stuff that you want to do. It's the parametrics. It's the topology optimization. It's the mass properties. It's doing motion analysis. It's doing finite element analysis. And so hopefully you can sit there and say, you know, if we really get organized and we really identify